Welcome to this video on circle theorems. We have here 4 exam questions we're going to go through. Some of them are quite tricky, and if you want to have a go first, pause the video and then rerun it to see the answers. Now, with these sorts of questions, just be aware the diagrams are rarely drawn to scale, and that can be very confusing. Okay, and you'll see some examples of that during this video. So let's start with this question. We have a cyclic quadrilateral here. That's a quadrilateral where all 4 vertices touch the circumference of the circle. And in that situation, opposite angles add to 180 degrees. So we begin by saying that 4x plus 7, okay, that's the angle at the top, plus the one opposite, which is 4x minus 3, add together to give 180. So we're going to form an equation and solve it to find x first of all, you see. Well, if you process that, you get 8x plus 4 equals 180. Okay, and therefore 8x is 176. And if 8x is 176, divide both sides by 8, and you get x equals 22. Okay, and what we've used is the fact that opposite angles in a cyclic quadrilateral add to 180. So that's what x is. But what are the angles? Well, we just have to substitute x equals 22 into each of the equations. So 4 times 22, okay, plus 7 makes 95. That's the angle for the top one here. Okay, and we already know that the other one opposite would be 85. Okay, but for completeness, let's show the working for that. 4 times 22 minus 3 is indeed 85, which is what we would expect. And to find this third angle over here, we've got 3 times x plus 20, okay, which is 66 plus 20, 86. Okay, and if that one's 86, then this one is 94, because it comes from 180 minus 86, okay, which is 94. So that's full working out to show the 4 angles, and from that, of course, we can easily see that the smallest angle is 85. So smallest angle equals 85 degrees. Okay, and the working out is clear and supports that answer. Okay, next question. Now this one involves a triangle, an isosceles triangle inside a circle, and we have an angle of 64. What we've got to find is the angle PRU, which is this one here. Okay, now we need to find other angles on the way. This is what I would do here. I would notice first of all that this angle is 64 as well, and that's because of the alternate segment theorem. So I'm going to say that angle RPQ, this is my working, angle RPQ, okay, that's the one I've just written in, is equal to angle QRV, okay, QRV, okay, and the reason that that's equal, and they're both equal to 64, is because of the alternate segment theorem. Okay, so that's the reason I'm providing for that answer. Alternate segment theorem. Okay, now I'm going to say that the angle here and here are both the same. Okay, and the reason they're both the same is they're base angles of an isosceles triangle. So for the next part, I'm going to do that angle, let's do this one here, PQR, So angle PQR, it doesn't really matter what order, PQR is equal to the angle PRQ, okay, and they're both equal to 180 minus 64, okay, which is the one at the top, divided by 2, okay, because of the fact that they are angles in an isosceles triangle, okay, and that comes to 116 over 2, which is 58. Okay, and I'll put those in there now, 58 and 58. Okay, and for my working out, I should have reasons, and I've used two things really, that the base angles in an isosceles triangle are equal, and that the angles in a triangle add to 180. So both of those two reasons have been used here for that part. Now we come on to the final part, and the easiest way to answer this is just to use the alternate segment theorem again with this one to here. I could also use the fact that I've got three angles on a straight line, and either way this one would work out to be 58. Okay, so that's always reassuring if you can find more than one way of getting the same answer, but I just need to conclude by saying that angle PRU equals 58 degrees, okay, and the alternate segment theorem has been used for that, okay, again. Okay, right, next question. Now this one here has quite a lot to do, and it's very easy to get confused with a question like this, so I'm going to take you through very carefully. Now you need to sort of stand back and sometimes turn the page over and sideways, look at it from different ways, because you're being asked to find the angle BDC. Okay, BDC. So B to D to C is this angle here, going up from B to D and then across to C. Okay, so that's the one I need to find in there. Now, if you look at the diagram carefully, we already have an angle equal to that, because it's this angle here from C to D to B is the same as this angle here from C to A to B, because they're both coming from the same 2 points up to the circumference and back, up to the circumference and back. So that's 65. So this red angle I've drawn in here is also 65, and the reason they're the same, so I need to just say that equals 65 degrees, okay, because angles in the same segment are equal, okay, and that would easily be missed. You could have spent a long time working out other angles first before you got to that, but that's the quickest and simplest way. Okay, now you've got to find angle ACB. ACB. Now the first thing I'm going to notice, I'll put this in a different color, so this is a right angle here, okay, and the reason it's a right angle is because it's an angle in a semicircle, okay, and if that's a right angle and that's 65, angle ACB is going to be 180 take away 90 and take away 65, which is equals 25 degrees, okay, because the angles in a triangle add to 180. So what I've done is I've used two things. I've used the fact that angles in a semicircle equal 90, or the angle in a semicircle I should say, and the angles in a triangle add to 180. Okay, and finally AOD, A to O to D. Now that forms an isosceles triangle, okay, so let me just highlight this in a different color. So this is from A to O to D, Okay, there. Now, that's an isosceles triangle. These two lengths here, I'll put this in a different colour. That length and that length are the same because they're both radiuses of the circle. All right, so therefore, if this is 44, this angle from here all the way round to here, okay, right up to there, is 44 as well. Base angles of an isosceles triangle are equal. And if those are both 44, the one that you're left with here is going to be equal to 180, okay, take away two lots of 44, okay, which is 180 take away 88, which is 92. Okay, now it doesn't look like 92, it looks like less than 90, but as I said earlier, these diagrams often do not reflect the true picture because they're not drawn accurately. All right, so you just have to be aware of that. So that's the angle AOD, which is 92 degrees, and the reason for that is that the base angles of an isosceles triangle are equal, and that enabled me to work that out. Okay, and it does say giving reasons for your answers. We had to do that all the way through. Okay, next question, and here we have a proof to do. Okay, now we've got to prove that these two triangles are similar, and to be similar, that means they're the same shape but different sizes. In other words, they have the same three angles as each other. So I need to carefully set this out. So I'm going to say that, first of all, that angle there is the same as this one here. Okay, and I'll just write that down. So angle ABC is equal to angle, well, I can call it, actually it's better to call it ABE rather, because it's come from there. So if I just do that instead, it would be right to leave it as ABC, but it's better to put ABE, okay, because that's showing the 2 points it's come from. It's the same as angle ADE, okay, ADE, and the reason they're the same is because they are angles in the same segment, okay. And I can do a similar thing for these angles here. These both come from the points D and B, so I've got DAB or BAD and BED. So I can say that angle BAD equals angle BED, and the reason that they're equal is the same as the last reason, that they are angles in the same segment. Okay, angles in the same segment are equal. Okay, now we come to the third pair of equal angles, which I'll put these in a different colour. So that's that one and that one. They're equal. Nothing to do with circle theorems. I can just say that angle ACB, so angle ACB is equal to angle ECD. Okay, and the reason that they're equal is they're called vertically opposite angles. Okay, vertically opposite. So there's three angles with reasons that we've compared. Now, using that information, we can conclude that triangles are similar. Triangles are similar, and an abbreviation that we are allowed to use is AAA, angle, 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 because effectively we've shown that they all share the same three angles. Okay, now the next part of the question, that was part A. Okay, part B requires us to calculate the length CD. Now I'm just going to put some numbers on here. So we'll have the numbers given. So AB is 5.2, okay? And this one over here, DE, is 7.8. Now, those are corresponding sides to the two triangles. Okay, and so we need to look at the scale factor of enlargement between that one and that one. Now, 7.8 divided by 5.2 is exactly 1.5, or 3 over 2. Okay, so in other words, this triangle is 1.5 times bigger than this one. Now, this is where you've got to be really careful with triangles inside circles, because they're saying that BC is 4.6, and you've got to find the length of this here, CD, which I'm going to call X. Now, if you're working with parallel lines, if that line AB was parallel to ED and nothing to do with circles, this angle here would be the same as this one over here, and this length here, this 4.6, would be scaled up to be this length here. But it's not, because it's all flipped over. The 4.6 and the 5.2 have the red angle in between them. The 7.8 and the X have the red angle in between them. So this X is simply going to be 3 over 2 times 4.6. Okay, and that is 6.9 centimeters. Okay, and that's the answer to the question. Okay, so I hope that was helpful. That's the end of this video on circle theorems.